Welcome. Today we're going to be looking at delta modulation. So delta modulation is an analog to digital signal conversion technique used mostly for the transmission of voice information. Delta modulation transmits the change in the information in the input signal and transmits it as a 1-bit data stream, where a 0 represents a decrease and a 1 represents an increase. So put in other words, rather than quantizing the actual values of the input signal, delta modulation quantizes the difference between the current value and the previous value, and sends a discrete bit representing the up or down change. So the way delta modulation works is we take the analog signal and we approximate it with a series of segments at a fixed interval. This is also known as the sampling frequency. So we can apply the sampling frequency to our example here. We'll just say we'll sample at this interval. So let's just pretend this is drawn in evenly spaced intervals, which represents our sampling frequency as we talked about. Now, the change in information is measured as a fixed increase or decrease of the signal amplitude based on the previous sampling point. This increment is known as the step size. Applying the step size to our example, we start at the origin, and we see that we're already at the signal in the beginning. So we just stay at 0 for the first sampling frequency. Now at our next point, we can see that we're much below the original signal now. So we'd actually go up by our step size. Similarly, we'd continue on, and at the next window, we'd again check if we're above or below, and we're still below, so we'd continue going up. And now if we check, we're actually above the original signal. So now we'd actually come down by our step size and continue on. So now that we have filled in our step size, we can see that we have a graph that sort of represents the original wave signal that we had. Now this is what we would actually transmit using delta modulation. And as we talked about previously, we're going to transmit just bits of zeros or ones. So what that would look like in our case is, first we have just a 0, and then we go up, so that's a 1. Then we go up again, that's a 1. Then we go down, that's a 0. Then we go up, that's a 1. Then we go down, 0, 0, 0, 0, 1, 1, 1. Now the receiver would receive the bits zeros or ones in a stream as we've shown here. And from this, they can actually decode the original signal, or at least an approximation of it, because the step size and the sampling frequency would be known to the receiver. So based on if it got a 0 or a 1, it knows how much approximately to go up by or to go down by, which would recreate an approximation of the original wave that we have. So delta modulation seems pretty cool and all, but why do we need it? Well, delta modulation was actually introduced in 1940s as a simplified form of pulse code modulation, which we've all learned about. Because pulse code modulation was too difficult to implement for an analog to digital converter.
So now let's talk about the pros and cons of delta modulation. So let's start off with the pros of delta modulation. So first off, you can really easily get a very high signal to noise ratio if you get your step size and sampling frequency just right, or alternatively if you use a technique called adaptive modulation. Another pro of delta modulation is the very low bandwidth. That says bandwidth. Very low bandwidth, because you're only using ones or zeros as opposed to the full spectrum analog. And a final pro could be that because you're only dealing with these ones and zeros, the delta modulator and transmitter are very less complex. So again, because you're not dealing with that full analog spectrum signal, just the ones and zeros, this really decreases the burden on your hardware requirements, and even just for your network engineers who are designing these networks, they don't have to worry about dealing with a whole bunch of wide spectrum signals. It's just ones and zeros. So now let's talk about the cons. So first of all, if you're dealing with very high or low amplitudes, accuracy is going to be a big problem. That's this accuracy. So basically, if you have a really big step size and you're approximating a signal that's very small, it's not going to be a very accurate approximation. And similarly, if you have a very small step size and you're approximating something that has very high peaks and dips, again, you're not going to get a very accurate approximation of that. Another con is oscillation. So because you're only saying that a signal is either going to go up or down by the step size, if you have a constant signal that you're trying to approximate, you're going to end up going above it, and then below it, and then above it, and then below it. Final con for delta modulation is the fact that you're dealing with this constant step size. That's this constant step. So basically, if the step size is too small, you're going to end up using too much memory to store this, and you're going to get something called slope overload. So basically, your step size is too small to approximate the signal, and your approximation ends up really bad, and you get a lot of noise with it. On the flip side of this, if your step size is too big, you're going to get something called granular noise. So this happens when your approximation is really big and blocky above a nice small little analog signal. So this really doesn't sound good at all.
So, learning about delta modulation was cool and all, but now let's see it in action. We wrote a Python script to take an audio file, perform delta modulation, and then convert it back into an audio file so we could compare the two different audio files and see how the delta modulated version sounds to the original. Let's get right into it.
So now we're going to run a cover of Ed Sheeran's Shape of You through our delta modulation code. And once it's done modulating, it'll first play the original audio file, followed by the delta modulated audio file, so you can hear the difference between the two. So now that you've heard the original and the modulated audio file, you can see that they were pretty close, but the modulated audio file had some noise in it. And that's because we're recreating the audio file based on the data that was actually transmitted. So now let's look at the output that we got from our script. So most of the initial stuff is just facts about the file information. But what's interesting to us is what we see over here, which is the step size that we're using is 1536 and a sampling frequency of 1. And the reason for this is because we found that these two values gave us the best signal to noise ratio, which I'll talk about just in a few seconds. And we can look at the transmit data. We're only showing the first 100 data points because, again, the entire data sample is just going to be a bunch of ones and zeros. But you could see that it's just going to be a data stream of zeros and ones, where a 0 represents a decrement by the step size and a 1 represents an increment by the step size based on our difference between the actual and the modulated files. And now down below we can see that the compression between sending the modulated data file or the data stream of bits versus the original data is over 50%, which is huge when you're trying to transmit a file. This was just a 10-second audio clip, but imagine a larger file. And this compression rate would only get better if we were to increase the sampling frequencies from 1 to say 2, 3, 4, or whatever happens to work best for any given value. Important thing to keep in mind is that the step size and sampling frequency in this case are chosen uniquely for this given file, and you would have to choose different values for a different file if you were to try it out. And now down below we can see that the signal to quantization noise ratio for this file is 6.98, which is pretty high, and this was one of the best that we could get by playing around with lots of different step sizes and frequencies. Now lastly, let's look at a graph of the original audio versus the modulated audio and see how close the two mirror each other in this case. So we can see that the raw data is shown in the yellow and the delta modulated audio is the overlay on top in blue. And you can see that while in certain places it's kind of off, for the most part it's actually pretty close to the actual audio values that the file had. And we can see in certain points we get to the peaks and we come down, and while it doesn't go as far down as the original, it's pretty close to it.